feel like this is not that hard. I've double counted every edge, of course, right? Because every edge is on precisely 2 faces. Can I get vigorous head nods if you're good? Questions if you're not? Woo woo! Okay, so having established these sort of counting arguments regarding the things, then immediately I get from this that like 3b is 2e, and so the number of edges is just like 3/2 times the number of vertices. So how many edges? Yeah. Woo woo! And if there are 72 edges and 48 vertices, how many faces? Probably just like use Euler's, right? The number of faces is like 2 minus the number of vertices plus the number of edges. If I did that right, I think I did. 74 minus 48 is 26. 74 minus. Yeah, so there are 26 faces. That's like amazing. And we like count them to make sure that's true. Also, how many can I get? Also combinatorically, how many hexagons, octagons, and squares there are? I think I can do that too. How do I do that? I think I do another counting argument, right?
Also, if you have F, B, E now, so you can plug those in, and then you just have a system of equations, those 3 equations.
Yeah, but wait, I think it's even easier than that, right? Because I think if I just do like.
Wait, there are 48 vertices. And
Oh yeah, no. It's even simpler. Because if I just do every vertex is on how many hexagons?
1.
Exactly 1. Right? Every vertex is on exactly 1 hexagon. So if there are
so the number of hexagons is the number of
Is 48
yeah, the number of hexagons is the number of vertices divided by 6. Right? Yeah, maybe it's clear if we just say it like this, right? Count if you take the number of hexagons times 6, then that counts every vertex exactly once. Agree? So then H is 8. There must be 8 hexagons. And yes, question.
How did you know that
T is always 720. That's the theorem. T is 4 pi. Yeah, good. Good. And again, if I count the vertices by saying there are 4 vertices per square, then I've again counted every vertex exactly once. So there are how many squares? 12. And how many? What's left? 8 times the number of octagons is also the number of vertices. So there must be 6 octagons. All right, that's like amazing. All right, good. Next, bottom of the page. We have 4 minutes. You do it now. Truncated icosahedrodecahedron. Go.
Which one is that? That's the soccer ball.
Not exactly. No, actually, just like not actually. This is the icosahedrodecahedron. The icosahedrodecahedron is the rectification of the dodecahedron. Alternatively, the rectification of the icosahedron. So, if you take the dodecahedron and you rectify, does everyone remember what that means? You truncate to the midpoint. So if you truncate to the midpoint, then you get a smaller pentagon for each pentagonal face in the original dodecagon, and then every vertex becomes like a triangle. Yeah. So this is the icosahedrodecahedron. This is the polyhedron that's hanging in the pandas playing chess mural in my wall of my apartment. Why are you doing that?
No reason.
Hiding camera.
Good. All right. So the truncated icosahedrodecahedron. What does that look like? Well, now by truncating it, every pentagon becomes a decagon, right? Every vertex becomes a square, and every triangle becomes a hexagon. Yeah, not memorize, understand. It's not memorization. which is this one right here. Boom. Good. While you're whining, Peachy's just doing the problem, which is good.
You are.
Good. Peachy says, aha, I have found you, my friend, the truncated icosahedrodecahedron. It is this guy. All right, how can one characterize an icosahedrodecahedron locally? The intersection of a decagon, hexagon, and square. Go. Perform the same counting argument. Figure out how many vertices, faces, edges, and then how many decagons, how many squares, how many hexagons.
Well, Elijah's like he's done. Yeah. Where are their degrees?
It's actually like amazingly like beautiful, wonderful, interesting, fascinating stuff. I did like
It's cool. But not.
I was just elated. I was dancing around in a cloud yesterday from like 11 a.m. until like still.
How are you getting 45?
Run to the bottom of the Good.
Wait, one comment with this.
We have squares.
What did I do?
What did I do, Steven?
What's the answer for myself?
144 is decagon.
Yeah, you have that.
And I believe this one has the smallest angular defect.
Of any
A very small angular defect. I think it's like 6, right?
Yeah.
Wow, spoilers.
How it is.
It's a freaking small angular defect. So therefore it has how many vertices? 120, which is the most number of vertices of any of the Archimedean solids, I believe. Alright, good. Finish this packet. Actually, it gets a little bit more complicated. We'll do the rest of it like some other day. We're going to have a test next week, Wednesday, Thursday, Friday. Woo! Tomorrow all juniors are gone.